Well, I like to work with conceptual models, at least some of the time. For me, that's the most fun thing. Models where you try to understand. Are you hearing funny effects? Or that's just the echo here. Okay. Great. Where you try to understand things, how things work physically, rather than necessarily trying to get a quantitative answer. And so when I have my hour later in the session, I'm going to give you a research example where I did that. But here I kind of want to give more of a teaching example to just show you guys what the method is and why I think it's important. So we're going to be thinking about snowball Earth episodes. And in David's talk this morning, you could see that where he showed the increase or the changes in gases in the atmosphere, you could see that there have been two eras where there were big snowball Earth episodes where Earth was either covered in ice or nearly covered in ice. And those seem to be correlated with major changes in the atmospheric composition and potentially with major changes in evolution in the types of organisms that you find on the planet. So they seem to be important in Earth's history. And similarly, there's been a lot of thought recently about cycles between snowball Earth periods and warm climate periods near the outer edge of the habitable zone. And so we're just going to make a simple conceptual model that can explain how these things work. So imagine the planet is zero-dimensional, just a dot. That'll be easy for you astronomers. And let's say we want to understand the temperature of the planet. So we have some heat capacity times the derivative of temperature with time, dt dt, d big T dt. And so this is sort of how the temperature of this dot is going to evolve. So does anyone know what are going to be the terms involved that are driving changes in temperature? Okay. Who said that? Albedo, yeah, okay, but why is the albedo important? Well, it's important because what increases the temperature is the shortwave radiation from the star. So the solar flux, and how does this dot cool? Yeah. Okay, so it's emitting radiation to space. So it's absorbing short wavelengths from the star, and it's emitting in longer wavelengths just because it's a black body. And so we can write this. One way we can write the absorbed solar flux is, like Mike said, involving the albedo. This is usually how it's written. So we can say there's some amount of radiation from the star that's hitting the planet, and this is the amount that hits a watts per meter squared of space at that distance, and then you divide by 4 because there's an intersection of pi r squared and a surface area of 4 pi r squared. This is what we call the albedo, or the reflectivity, and it's the same as, what's his name, Albus Dumbledorfer? What is that his name? Dumbledore? The guy in Harry Potter, isn't it? Yeah. Thank you. So Albus means white, and he has white hair and white beard, and this is the whiteness of the planet, the reflectivity. So we take 1 minus the reflectivity times the solar, and then for emission to space, we'll just linearize like this. Okay? And it turns out that FL is more like something like this. So it's more like some kind of emissivity and a sigma t to the 4th. But because of the water vapor feedback, this linearization, which changes the emissivity, linearizing a t to the 4th is actually much better than you could expect it to be. So this is not a terrible approximation. Okay, so that's our model. This is our planet. And the one key thing is that we're going to include what's called the ice albedo feedback. And so we're going to say that when it gets colder on the planet, you're more likely to have ice, and so you're more likely to have a higher albedo. So we're going to say that the albedo, so if we plot temperature and the albedo, at cold temperatures, it's got some value called alpha cold. And at high temperatures, it's got some other value, alpha warm. And then there's a transition temperature that has something to do with the freezing point. Let's say that it's T equals 0. It could be a little different because there's a seasonal cycle. And then there's some transition between them. So this is going to be our function for the planetary albedo as a function of temperature. This width, delta T, this tells us about, this results from the fact that we've taken a three-dimensional planet and put it into 0 dimensions. So if some of the planet is glaciated and some isn't, you're going to have an albedo intermediate between a globally glaciated and a warm state albedo. Okay? And so now we're going to solve this thing. So first, let's just do a plot, a phase diagram. So let's see how C d temperature dt behaves as a function of temperature. Okay, so for anywhere where there's a constant albedo, this thing is just a decreasing function of temperature. So it's going to do like this. And then we get this transition region where it goes up again, and then we have another constant function of temperature. In each case, the slope is minus b of these two lines, and this results from this sigmoidal joining of the two albedo regimes in the two different temperature regimes. And so here the albedo is the cold value. Here the albedo is the warm value. This distance is approximately 2 times delta T. And then here, this is about temperature equals 0. And the way that you interpret a plot like this is if you're sitting on the line here at some temperature, here dt is positive, so you have to be going this way. Here it's negative. Here it's positive. Here it's negative. And if dt intersects 0, that means you're going to stay at that point. And so these are all stable, these are all fixed points, these three, which means you would stay at them if you're on them. But these two are stable, which means if you perturbed away from it, the system's going to bang you back towards it. And this one is unstable, which I'll draw with a little circle. And so the first thing that you can immediately notice is that there are two, at this particular solar forcing that I drew, so you could imagine varying this solar forcing. There are two different stable states, one that's warm like modern Earth, and one that's a snowball Earth, that's a globally glaciated Earth. And then there's an unstable fixed point that acts as a separatrix. So if you start on this side, you go to the warm state. If you start on this side, you go to the cold state. And so, and the basic physics behind this are this ice albedo feedback, that ice has a higher albedo, more reflectivity, which makes things colder, and that ice likes to exist when it's colder. And so you can get a stable state where it's cold and it's high albedo, so it stays cold. And here, it's warm and it's low albedo, lots of absorption, so it stays warm. And so that's what sustains these two different states. Now, if you took this solar flux and you, okay, so first I'm going to draw that again. Okay, so we have a curve that looks like this at some solar flux. If you increase the solar flux, if you look at this, what that's going to do is it's going to shift the entire curve upwards. And so if you increase the solar flux, you can get a curve like this. And what's happened there is there's been a bifurcation where if you were sitting in the cold state, as you increase the solar flux, the cold state joined with the unstable separatrix state, and they disappeared in a saddle node bifurcation, and you jump, and so now only the warm state exists. And if you decrease the flux down, you can get into a situation where instead you lose the warm state. And so now only the cold state exists. And because of this, you can get a hysteresis. And so if you started in the cold state, warmed up, and jumped into the warm state, you would have to decrease your solar forcing more than you initially increased it in order to get back into the cold state. So that's called hysteresis. And because of this effect, so initially when people noticed in the climate equations that this sort of a solution existed, a globally ice-covered solution, they thought that we could never have gotten into it. Because if we had, this hysteresis was so large that they didn't know a way that we could get out of a snowball state. And it was only later when people started thinking about the carbon cycle and weathering. So on Earth, we have CO2 being put into the atmosphere by volcanoes and removed by weathering reactions, and realized that those weathering reactions require warm water and wouldn't work in a snowball Earth, that there was an idea for how to get out of it. And the idea is that because the weathering reactions shut down, you just build up CO2 to immensely high values so you can get over this hysteresis. And now we can put together all of this if we solve. So essentially these steady states we can find by solving and setting this equal to 0. So we can say that at t equals t star, you have steady states or fixed points, and their solutions to dt equals 0. So their t star equals 1 over b times 1 minus alpha of t star. I'm going to leave it like that for a second. Times S0 over 4 minus a. So this gives us the solutions. And this guy, most of the time, this is either alpha cold or alpha warm. And there's some region for the unstable fixed point where you actually are going to have to iteratively solve this, or use some method to solve this, because it's going to be potentially a transcendental equation. Okay, and so now we can plot this in what's called a bifurcation diagram. So we can plot this thing we're interested in, t star, as a function of our forcing variable, where our forcing variable is the solar constant, S0. And so this would be t star equals 0. And at cold temperatures, we're going to have a value of alpha c here. Alpha c is high, so that means that 1 minus alpha c is low. So we're going to have a relatively low slope, like this. And then at warm temperatures, we're going to have a value of alpha warm here. Since alpha warm is small, this is going to be higher, and we're going to have a steeper slope, like this. Okay, so this slope is 1 minus alpha w over 4b. And this slope is 1 minus alpha cold over 4b. And those are the easy parts where alpha, yeah. Oh, okay, I'm almost done. Where alpha of t, is that 3 minutes until questions or 3 minutes total? Oh, okay. So here, these are the two lines where alpha of t is a constant, where you're in one regime or the other. And then there's sort of, you have to join them together with the unstable solution, which you could solve for numerically, or you could just stick it in, and it's going to look like that. And so this tells us, if we varied our solar constant, how we would expect such a planet to behave. We might start up here, and we would decrease the solar constant or the CO2 or something. You would hit this. You can see this is a bifurcation. We've got the two, a stable and unstable fixed point, joining and disappearing. And then you would jump. So this part you could stay along that curve for this part of the cycle. But once you hit here, you've got to jump over to here. And then if you increase the solar constant again, and here's where the hysteresis comes in, where you have two stable solutions possible at the same insulation. Eventually, you would hit this bifurcation, and you could do cycles like this, if you could vary the solar constant as a free parameter. So anyways, this is the kind of way that I like to think about problems, at least some of the time. So if I do fancy numerical calculations, I like to then stop and go back and try to understand things like this. For anyone who's sticking around for the next 5 weeks, I'm going to give a talk like this, but on an actual research problem at some point. I don't know when that's going to happen. Okay. Yeah, not much. So this is the issue. So if you look at the habitable zone, this is a pretty funny problem. So suppose you do the naive astronomer estimate of the habitable zone. You would pick a constant albedo, something, and you would not include the water vapor feedback or the ice albedo feedback. And if you do that, which I've done, you get almost exactly the limits of the casting habitable zone. Okay, which is kind of interesting. But climate scientists put in the ice albedo feedback and the water vapor feedback, the fact that there's more water vapor in the atmosphere when it's warmer, and so you have a stronger greenhouse effect, both of which are positive feedbacks. And when you do that, the habitable zone narrows, so that if you do this in a fancy climate model, it's something like 5%. You decrease the solar constant by 5%, you go into a snowball Earth. And so it's really extreme. You have a very narrow habitable zone. And then it's only because of this weathering feedback that regulates the CO2 that you can have a wide habitable zone. But it's sort of 5% will get you into snowball Earth at a constant CO2. Yeah?
How would you add in something like a cloud albedo?
Well, in this model, the only way you can add it in is as a simple function of temperature. So you would have to think that at some temperature, the albedo changed. Implicitly, the cloud albedo is included in this model. If you say that your warm temperature albedo, if it were just water, it'd be like 0.1. But usually in a model like this, you'd use something like 0.3 because you think that over the water there's going to be clouds. Exactly. Exactly. Well, you could add another bifurcation, for example. So suppose someone talked about the stratus clouds yesterday, one of these days. So there are large stratus decks. Oh, that was at lunch. Never mind. There are large stratus decks in the subtropics of Earth. And one of the main sources of uncertainty in climate forecasts is that different models either say these stratus decks, and they reflect a lot of radiation, are either going to stay there or go away. That's a big part of the spread in global warming forecasts. And so if you thought these were going to go away, that's a positive feedback, and you could add that into the system, and you could get another buckle and bifurcation. Those sorts of bifurcations are always going to be small and high order compared to this basic thing of covering the entire planet with ice. Yeah? Yeah. Yeah. Oh, it doesn't. No, that's just, if you did that, you would go through a cycle. If you considered solar forcing as an external parameter that you could vary, you could make this happen. Now, in the cycles that people have been talking about for the outer edge of the habitable zone, they work a little differently, and basically those cycles are at a constant value of the insolation. And what's going on, that involves the weathering. And so what's going on with those is, our idea with chemical weathering of CO2 is that it's a function of temperature, is the simplest way to put it. And so imagine that at your coldest temperature before you enter your snowball Earth, so we could stay in this stable point if our weathering can balance the CO2 outgassing, then the planet's going to be happy. But if our weathering is greater than the CO2 outgassing, the planet's going to keep cooling. So if at your coldest point before you go into a snowball Earth, your weathering is still larger than the CO2 outgassing, then you're going to jump into a snowball Earth. Now imagine that your weathering in the snowball Earth is less than the CO2 outgassing. That's going to cause a cycle like this. Yeah? Yeah?
Yeah.
Yeah. Yeah, I mean, yeah, so it turns out that for the snowball transition, it's unlikely that for an Earth-like planet, the variation during an orbit could have a huge effect. And the reason is that the ocean has a fairly significant heat capacity. And so to cool the ocean, the upper ocean up enough to cause a snowball transition based on the variation in insulation you'd expect on an eccentric orbit is probably going to take 50, 100 years. But the orbit should be quicker than that if it's going to be potentially Earth-like. So there are, potentially you could get situations where, I forget which one's aphelion. Perihelion's far away. A is away. Well, never mind. I can't keep those straight. So at the close-in, when you're warm, you could be unglaciated. And at the far away, you could be glaciated, potentially. But it's pretty hard to get that to work if you have an ocean, because the ocean has such a high heat capacity. It's hard within one cycle to get that to work. Yeah. Because the time scale of adjusting the ocean is longer than a cycle, even for any sort of reasonable Earth-like. It could happen. It's not impossible. It's just not. It would be sort of like a special case.